From Diamond Light Source, this is the Diamond Podcast.
Hello and welcome to the September edition of the Diamond Light Source podcast. This month, we shed light on the field of X-ray imaging to discover a new beamline offering insight that was never possible before. And that's the Imaging and Coherence beamline. We'll be exploring how the new technique can be used to improve the recycling of metal alloys, and also to explore whether we really can safely hide away our carbon dioxide emissions deep down in the rocks below.
The brine, as I've said, likes the narrow bits of the pore space. It fills the small pores and the nooks and crannies. It leaves the CO2 behind in the big pores, and it surrounds the CO2. So you have bubbles, clusters of CO2, surrounded by brine. And then you can push as much brine as you like. That CO2 is not moving. It's not going anywhere.
Martin Blunt will be explaining how his team are exploring the potential of injecting carbon dioxide deep underground, and whether once there, the carbon will stay put, later in the show, when we also bring you the latest research, news and events from the light source. So all that coming up in this edition of the Diamond Podcast, with me, Mira Senthi-Lingam.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
This month, we're taking you to the cutting edge of synchrotron science, as we explore Diamond's new Imaging and Coherence beamline, where X-rays will soon allow scientists to see with greater clarity than ever before. The beamline goes into operation in October for use across a wide range of scientific disciplines. Graham Morrison chaired the user working group for the beamline, and he explained just why the imaging offered is so unique.
There are three ways in which images can be formed, and X-ray imaging has been a long-established technique ever since Röntgen discovered X-rays at the end of the 19th century. But the three principal ways are to form a shadow projection, like a hospital radiograph, where you simply have a parallel beam of X-rays going through the sample and you get absorption by certain areas, and so you get areas of light and dark. A more sophisticated method is to use some form of lens, and with X-rays that is already a challenge because X-ray lenses are quite difficult to fabricate. With a lens in place in the beam path, effectively you can get magnification, and so instead of just getting a life-size image or a one-to-one image the way you would normally with projection, you can get a magnified image of the object you're looking at. And the third way that's newly being developed and explored over the last few years is a process known as coherent diffraction imaging, where essentially you don't try and form an image directly. What you record is the diffraction pattern from the object, and then you use computer algorithms to try and reconstruct the image from the diffraction data that you've recorded. Now, because that doesn't involve any form of lens in the beam path, it means that you're not limited in the same way that you are when you're using lens by the technical capabilities of the lens. And so in principle, you can get much better resolution from those reconstructions, but it does depend on the reliability of the algorithms that are used for that process.
And this latter process then, using diffraction patterning, that's what the new Imaging and Coherence beamline at Diamond will be taking on board.
The Imaging Coherence branch is intended to do both conventional imaging and to use this new approach of coherent diffraction imaging, as it's called. And so there are two branches on the beamline I-13. One branch, the imaging branch, obviously, will do the shadow projection imaging, which is a very straightforward technique and can yield very useful information. It allows you to look at samples with a big field of view, so that means you can look at perhaps millimetre-sized objects.
But this new beamline, it does have two branches. It has the imaging and the coherence. And what I guess is quite different or unique about the coherence side of things?
The coherent diffraction imaging branch, which is if you can record the diffraction pattern successfully and then use these computer algorithms to reconstruct the image, that will take you down to about 5 nanometers, which is much higher than you can achieve with any focusing optic. And so again, it allows you to address a new range of samples, or get new information about samples that is not currently readily achievable. But traditionally, until now, or until very recently, that's been limited. But a new method that's been developed in the last few years, known as tychography, developed principally by John Rodenberg at the University of Sheffield, has allowed the coherent diffraction method to be extended to look at much larger areas of sample. And the idea is that you illuminate produce a spot of X-rays on the sample, you've recorded a diffraction pattern from that area, and then you step the spot over the sample so that each successive diffraction pattern comes from an overlapping area of the sample. And it turns out that if you do that, then the methods of reconstructing the image data from the diffraction pattern works much better and converges more quickly to a reliable answer. And so this allows you to get lensless imaging of samples at very high spatial resolution and also to look at extended areas of samples. So I think the application of this sort of approach on the coherent diffraction imaging beamline will be a very important development.
How would you then just summarise the main benefits of this new beamline and the fact that it has these two branches?
In a sense, it's covering such a huge range of length scales, from the millimetre scale with the projection technique right down to the nanometre scale with the coherent diffraction and imaging and tachography. As a result, it's also going to cover a huge range of different types of sample, from sort of engineering materials down to nanomaterials. I think it's actually a beamline that will be attractive to a whole range of users.
Graham Morrison, Chair of the User Working Group for Diamond's Imaging and Coherence Beamline. And having heard about the extra possibilities this technique could provide, I went along to see it in person and learned just how the X-ray beams are manipulated to such specificities from the principal beamline scientist, Christoph Rau.
So we are at the beamline R13 for imaging and coherence, and the purpose is imaging to image on the micro and nano length scale.
So we're currently just out on the actual outdoor grounds of Diamond, and the synchrotron is quite a distance away from us. We can see it. So we're now about, maybe 150 metres or so away. So this beamline is quite unique in itself in that it's located out of the light source. It's at this distance of, I think the hutch over there is about 250 metres?
That's correct. The reason for doing so is we want to make use of the property of coherence of light. And for doing so, you have to have a very small light source, and B, to be very far away, to have a large lateral coherent field, and that's exactly why we are so far away.
So what do you mean by coherence?
Coherence is a property of light. Light might have different characters. One is the feature of being a light particle, or light might be considered as a light wave. And then in this case we talk about coherent light.
So by coherent light, you mean light in its wave form, not particle?
Correct.
And well, how is a beam of light maintained at such a large distance? So we're currently about halfway between the light source and the beamline hutch. So we're about 150, maybe 125 metres away. We're stood on top of concrete, and below us, within this concrete, are the tubes, I guess, in which the beam of light will be travelling. What happens at either end of this tube to keep this light travelling straight through?
Okay, at the beginning we have the light sources, which are ondulators, and each ondulator generates the X-rays, and they are canted to each other in a slight angle. And further they propagate down the beamline, more they get separated. And to increase further the separation, we put some mirrors at the beginning of the beamline, so that at the end, where we are standing here now, we have roughly a separation of 4 meters between the two different branches.
So you have two beams of light coming over to the hutch here from the source?
That's correct, yes.
So if we just move into the actual hutch now to see the type of research that can take place at this beamline. There are two hutches at this beamline, an imaging and coherence one. We've come through to the imaging one, but what kind of imaging will take place here?
So on this branch, we have now the partially coherent light arriving on the sample, and while the light is going through the sample, the light wave is deformed, and what happens is that around the edges of the structures get enhanced, the light wave is deformed, and then you can easily detect with the detector these enhanced structures.
Therefore, I guess, quite clearly seeing the edges and therefore the shape and structure of your sample.
That's correct, and that's what's called then the edge enhancement.
So, and what kind of samples will be looked at in this way?
Well, basically any kind of sample which is opaque for the eye and which has interesting features on the micron length scale. Applications are in the field of biology, for example, material science, geology. There's a very large range of applications.
And how does this compare to other imaging techniques, say even those used in hospitals, so just a simple X-ray?
The big difference is the resolution you can achieve. While at the hospital, for example, the doctor is interested to learn about whether the bone is broken or not. Here we are interested in questions like, why does the bone break? What is the mechanism behind this? How can you improve any kind of mechanical behavior? And so on.
Now, this is the imaging hutch, but as you mentioned, there are two branches for this particular beamline, also a coherence one, which is about, say, 4 to 5 metres away from here, but in another hutch. What kind of work will be taking place? What will be looked at there?
So here, for example, on the imaging branch, we will do biomedical applications and material science. So we're interested, for example, to learn about cracks in material. That's very important for industrial applications. Or for biomedical applications, what I'm personally interested in is a lot to learn about hearing. We will study then the mechanism which are happening inside the cochlea.
Christoph Rau, Principal Beamline Scientist at Diamond Imaging and Coherence Beamline. Now, before we move on to find out about the actual research that will benefit from the new technique, we first join Sarah Boundy from Diamond's communications team for the latest news from the light source, starting with some eye-opening research.
Yes, a group has been studying the microstructure of the peripheral cornea. The cornea is the external lens of the eye. It's responsible for refracting incoming light onto the crystalline lens behind it, which in turn focuses it onto the retina. To function, the cornea needs to be transparent to visible light. It also has to possess high mechanical strength and have precisely defined curvature to focus. The research was carried out by a team from Cardiff University, and they're using Diamond's non-crystalline diffraction beamline I-22 and also the ESRF in Grenoble, France. And their results were recently published in the Biophysical Journal.
And so what were the scientists looking into about it?
Well, they know that 90% of the thickness of the cornea is made of something called the stroma, which is a thick, transparent layer primarily composed of collagen fibrils. So the shape of the cornea is thought to be strongly influenced by the arrangement of collagen fibrils in the stroma and surrounding tissues, and it's this knowledge that is key to understanding how corneal disease and surgery can affect vision.
So I guess by having a good insight of the structure, you can see how disease perhaps damages it, and also when reconstructing it, say with surgery, you'll have a better idea of what needs doing.
Well, that's right. Their results showed that the fibril diameter is constant in the centre of the cornea, but increases rapidly when moving out towards the periphery. So this may be an important factor in understanding how the cornea responds to surgery involving peripheral incision, for example, cataract surgery. So one of the side effects and complications is astigmatism, and this research will help to explain observations by clinicians that the extent of astigmatic changes depends on the location the cut is made.
So very useful in the post-surgical time as well, I guess, after corneal surgery. But as well as, say, the eye, scientists here have also been looking at viruses.
Yes, the group has used one of our macromolecular crystallography beamlines, IO3, to look at the ancestry of viruses. So this is research carried out by Oxford University's Wellcome Trust Centre for Human Genetics, and it was published recently in Structure. Just as humans have an ancestry, so too do viruses. So the group are currently working on piecing together a complete history of viruses by solving the 3D structures of the virus proteins.
So is not much known then currently about viral structures?
Well, viruses are really large, complex structures, so it takes a lot of time and effort to solve the structure of the proteins involved in them.
And which viruses then have they been looking into so far?
Well, the group have successfully solved the 3D structure of the protein D13 from vaccinia virus, which is a member of the poxvirus family. So this protein is a scaffolding protein, and its particles, or virons, take the shape of a sphere as the virus starts to form, before D13 is lost and the viron takes on a more brick-like shape. And this is the first time they've been able to determine the structure of the protein D13.
And why is it useful to know, say, this particular virus structure?
Well, they found that it has a very distinctive shape, a shape that is also found in large DNA viruses such as human adenovirus, which is a cause of respiratory and eye infections. So by comparing the structural similarities of the different viruses' scaffolding proteins, they can determine the lineage of vaccinia virus and place it within their virus family tree.
And I guess an application then of knowing the structures is really then to possibly come up with better treatments as well, or antivirals maybe.
Well, exactly. Knowing who or what a particular organism is descended from can tell us a great deal about how it might function. So in the case of viruses, this kind of knowledge could help us to find new ways to treat them. We could be looking at drugs that could treat patients who are suffering from one of a number of viruses, just in the way that we use antibiotics to treat a number of bacterial infections.
So treating, I guess, a family of them rather than very specific viruses at a time.
That's right.
And now what about more in-house news for Diamond?
Well, we now have our summer 2011 issue of Diamond News. That's our biannual newsletter. So this one includes research looking at altruistic bacteria, metal organic frameworks for sustainable storage solutions, and tunable polymers, which are enabling scientists to create colours without using pigments. There's also a roundup of some of our PhD students in there and some updates on the facility as well. So there's lots going on. Copies are available from our website.
And as well as news updates, you've also got more multimedia content online now as well.
Yes, we've been working on some new video content. You can see the first instalment, which we've called We Are All Scientists, and that's on our website education pages. It features clips of scientists and engineers talking about what fascinates them about science and what they think of the Diamond synchrotron and why it's important to them.
Thanks, Sarah. Sarah Bandy from Diamond's communications team. And you can access the videos Sarah discussed, as well as plenty of other multimedia content, online at diamond.ac.uk.
Did you know it took Dorothy Hodgkin 12 years to solve the structure of insulin? If she were to do this today on one of Diamond's MX beam lines, it would only take 15 minutes.
This is the September edition of the Diamond Light Source podcast, and this month we're shedding light on the field of X-ray imaging. Still to come, we discover how scientists are imaging rocks found deep beneath the Earth's surface and calculating their potential to store carbon dioxide, something that, if effective, could prove essential in the battle against climate change. But first, we meet Professor Peter Lee from the University of Manchester, who's hoping to use Diamond for some clarity about the structure of metal alloys.
I study the solidification of metals, the processing of metals, as well as other materials. During that, there's all sorts of kinetic reactions happening and microstructures forming. So the strength of any alloy is not just in its composition, but that composition causes it to form small crystals, different phases, and those phases actually very often are nanostructured. So the strengthening goes from the scale of 10 nanometers, where you have small precipitates which are pinned. And in fact, in alloys, nano reinforcement has been used for over 103 years now. And that then evolves and goes up to the scale of microns and then into a structure at a scale of millimeters. I use Diamond in order to investigate the composition, morphology, and interaction of these different phases and structures.
And what particular alloys do you look into or focus on?
Well, one of the main ones I look at is aluminium alloys. These alloys are used from everything from automotive through to aerospace components. The bulk of these alloys in high-performance applications has been using primary aluminium. The reason they use primary aluminium instead of secondary or recycled aluminium is when we recycle aluminium, we almost as people end up slipping in various different steel components. It also just comes through when you break up and recycle an automobile. You end up with, very simply, nuts and bolts, which are almost always steel. We then remelt it. The iron concentration in the alloy goes up. Adding that iron concentration, as soon as it gets over 0.5 weight percent, starts causing another phase that, when it's very fine, can be reinforcing, but when it's large, can actually be detrimental to the properties. It forms a phase which is highly faceted. It has flat planar edges, sort of like a diamond, but the phase it forms, instead of being like a diamond, which is nice and chunky, is elongated or needle-like. Now imagine structures which are very pointy inside of a material. They act like stress concentrators, and so they can actually initiate creep damage and cause early failure.
And now, knowing this information, are you trying to see what's possible, I guess, to make recycled aluminium alloys more desirable?
Exactly. Well, these structures go from nano, and when they're nano, they're beneficial. When you start getting the iron level up, they actually can become as long as 200 microns, or almost a millimeter long. And it's when they're these long, sharp shards that they can be detrimental. What we're using diamond for is in order to determine how we can alter the composition, go through and add very small percentages of different alloy compositions, or add heterogeneous nuclei that will convert these from a few large structures to many very fine structures, and convert something that's detrimental into something that's actually beneficial within the alloy. If we can do that, we can make the recycled alloys as useful as the primary aluminium alloys.
And how much of a challenge, I guess, is that? What do you need to do to go in there and break then those long shards and increase the strength around there as well?
It's a tremendous challenge. These alloys have 6 to 8 different components. Each of these components are varied in weight percent from a few parts per million up to going to 1,000 parts per million. If you now think of a sort of combinatorial experiment where you're varying from parts per million through to thousands of parts per million with 8 different components, very quickly you can work out that it's actually billions of experiments you can perform in different compositions. What we're using diamond for is to directly observe the kinetics to determine what are the critical phenomena. It's a real challenge because the few things that we predicted that do seem to be probable aren't stable in molten aluminium. Molten aluminium had a great ability to dissolve many, many things within it. You also have to be able to make these particles at a very tiny size and get them into this molten melt, which means that you need to be able to have them fully wetted by the aluminium. So there's lots of challenges. We've got lots of great science to carry on doing.
But what are the benefits, really, of using increasing amounts of recycled aluminium alloys rather than primary sources?
The huge benefit of using recycled aluminium is that when you make the first original primary aluminium, it comes from digging up bauxite, reducing the bauxite to alumina, then taking the alumina, which is basically one aluminium atom, 2 oxygen atoms, reducing that. When you do that, each of those oxygen atoms is converted into a CO2 atom. You sort of consuming huge amounts of energy. All of that means that you're producing somewhere between 7 and 10 kilograms of CO2 per kilogram of primary aluminium. When you recycle it, you're really just remelting and also purifying it. That, in general, uses less than 0.5 of a kilogram, or 1/20th of the CO2 is released. That, if we can go through and convert just 5% of the world's primary aluminium production to secondary in new applications, which are high value added, it means we can save 13 million metric tons of CO2 per year.
That's quite a saving, simply by understanding the internal structure and chemistry of metal alloys. That was Professor Peter Lee from the University of Manchester. Now, that's almost the end of this month's podcast, but before we go, we explore another area of research that could prove essential in our fight against climate change, and that's carbon sequestration. The technique hopes to capture carbon dioxide from power stations, compress it into a liquid, and store it deep below the Earth's surface. If proven to be viable, it's estimated the technique could be used to store 1/5 of our total carbon dioxide emissions. Professor Martin Blunt from Imperial College London has been looking into the challenges of injecting these emissions into the ground.
Most of our research is concerned with carbon capture and storage, where CO2 is separated from fossil fuel burning power stations, compressed, transported, normally by pipeline, and then injected deep underground. And it's the injection and what happens to the CO2 deep underground that's the focus of our research.
What are the challenges associated with injecting, liquid carbon dioxide deep into the ground?
That's right. It is at very high pressures, so it's liquid-like. And what we're injecting it into is into porous rock. So I've got here a sample of a carbonate rock. The CO2 is injected into the tiny micron-scale pore spaces of this rock that initially contain brine. So the rock's full of salty water, we inject CO2. It's the same types of rock in which we find oil and gas. Indeed, we could store the CO2 in depleted oil and gas fields as well. The main concern that we have is when we inject the CO2, how can we ensure that it stays underground, that it doesn't escape to the surface? So what we're looking at is what happens to the CO2 when we inject it. Will it stay underground?
And so this model of rock that you've got here, this is calcium carbonate, the rock, yes. And it's just it's a reasonably small cylinder, I guess, a few, about 10 centimetres or so long. But why this particular rock?
The two major rocks in which we find both oil and gas and indeed the major storage of CO2 in aquifers are essentially carbonates. So calcium carbonate, the remains of seashells crushed and chemically altered over millions of years, and sandstones, right, which are mainly silica.
Well, you've mentioned that one of the key kind of challenges or issues on people's minds is whether this CO2 will stay down in the ground once it's there. So how have you set about investigating, I guess, how long it will stay there or whether it will be stable?
We've looked at the CO2 in the pore space of the rock at the micron scale. That's why we're using diamond. So what I have here is the special flow cell that we've used to study. So what we do is we take a very small sample of rock. I'm looking here now at a piece of rock that's about 5 millimetres across, about a centimetre, maybe a centimetre and a half long.
So a miniaturised version, really, of your cylinder earlier.
Yes, yeah. We're not just imaging the rock, we want to image the fluids. And what's new about this setup is we're imaging the fluids at reservoir temperatures and pressures. So the temperatures are about 50 degrees C, the pressures are about 100 times more than atmospheric.
This must be quite hard then to simulate.
Yes. So what we do is we take the little bit of rock, we wrap it in a sleeve very tightly, we inject fluids at high pressure. How do we contain all of this? What we do is we then have another jacket of water that's at high temperature and pressure, and we surround all of that with carbon fibres. Carbon fibre is extremely strong, thin, and it's X-ray transparent.
So just looking at the model here, so you've got this long kind of carbon fibre tube, I guess, inside of which you will put your sample. And on either end, you've got steel, larger cylinders. What role are they playing? Are they kind of providing, because they look like they've got connections coming out of them.
That's exactly what it is. So the bit in the middle of the carbon fibre is where the X-rays go. The steel at the end are basically to have ports through which we inject the fluids.
And this is essentially what you take along to Diamond to actually image directly?
Indeed.
So I guess what have you been able to see? So you've got these small samples of rock and you've injected various, I guess, amounts of carbon dioxide into them. What have you been able to image?
Right, so we can see on the computer screen here, this is an example here actually of a sandstone where we've had brine and we've injected the CO2. So we just look at the CO2 in the pore space and we can distinguish between grain, the brine and the CO2. And what we find is that the CO2 tends to move into the centres of the pore space and the brine clings in the narrow corners and nooks and crannies and the small pores. And the reason is the water loves the rock. Rock actually will soak up water like a sponge. The CO2 doesn't have such an affinity for the rock and tends to be in the wide pore spaces.
But then through your imaging, what you've seen is that you're pushing this brine, this water out, and the CO2 is getting stored in, but then the water's coming back in.
That's right. So we inject the CO2, CO2 goes in, can it escape? Well, the CO2 isn't quite as dense as water, so what it's going to do is it's going to move up. When it moves up, it moves out of a pore. What moves in? Brine. The brine, as I've said, likes the narrow bits of the pore space. It fills the small pores and the nooks and crannies. It leaves the CO2 behind in the big pores, and it surrounds the CO2. So you have bubbles, pore space, 10 micron to a millimetre size clusters of CO2 surrounded by brine. And then you can push as much brine as you like. That CO2 is not moving. It's not going anywhere. And that's what we can see directly on these images. We can see these trap clusters of CO2. And the beauty about Diamond is we don't just have two-dimensional images, We can do this in 3 dimensions, and we can see the 3-dimensional shapes of the clusters, but they fill about a quarter of the pore space. So what happens is when the CO2 moves, it leaves behind a trail of trapped CO2 and about a quarter of the pore space. That CO2 can't really escape because it leaves so much behind.
And I guess another challenge is you aren't able to see this over a period of thousands of years. So although you know that the carbon dioxide becomes trapped in this way, how can you be assured that it stays in this way?
What we can do is we can inject a lot of brine. We can't wait thousands of years, but we can inject so much brine that it's equivalent to waiting that long. That is, the amount of brine moving through is similar to waiting hundreds to thousands of years. And indeed, we've done that in this experiment, and nothing seems to happen.
And so what are some of the timescales of this? So the rates at which carbon dioxide will be injected and the rates at which brine will naturally move in?
Typical power station burning coal of 2 to 3 gigawatts is going to produce something around 9 million tonnes of CO2 a year. Inject that underground for a period of, say, 30 years, that's likely to create a plume of CO2 extending over tens of kilometres. What we could do is we could extract brine from the aquifer and then re-inject it to enhance the movement to trap the CO2. And the design would be that within 4 or 5 years, you've trapped virtually all the CO2, and you can walk away from that site assured that the CO2 is safely stored. Over hundreds to thousands of years, the CO2 will slowly dissolve. But when it dissolves in the brine, that CO2-laden brine is denser and it will sink in the aquifer. So it's a kilometre underground to begin with. It's just going to get deeper and deeper. And maybe over thousands to millions of years, the CO2 might react with the rock and form solid carbonate. What we're showing is that it gets trapped, it will then dissolve, it will react. And so it gets safer and safer. It gets less and less and less likely to escape over time.
So rest assured, it looks like the carbon dioxide might just stay there, as we hoped. That was Martin Blunt, Professor of Petroleum Engineering at Imperial College London. Now that is it for this month's podcast. But before we go, we've got news of a great new experiment that you can take part in. Diamond are carrying out a short story competition. The competition is called Light Reading and is encouraging scientists and non-scientists alike to use their imagination and write a story of up to 3,000 words, inspired by the facility. There's a £500 cash prize for the winner, and the deadline is the 30th of November this year. For more information and to enter, see the new website at light-reading.org. Otherwise, we'll be back in November with yet another podcast filled with the latest news, research and events from the synchrotron. Thank you very much to Graham Morrison, Christoph Rau, Sarah Boundy, Peter Lee and Martin Blunt for taking part in this month's edition. I'm Mira Senthilingam. Thank you for listening, and until next time, goodbye.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.